हेलो दोस्तों, वेलकम टू द साइनिंग ब्रेन। आज हम एनसीईआरटी क्लास 7 का चैप्टर नंबर 14 पढ़ने जा रहे हैं। चैप्टर का नाम है इलेक्ट्रिक करंट एंड इट्स इफेक्ट्स। यू माइट हैव ट्राइड द गेम हाउ स्टेडी इज योर हैंड्स suggested in chapter 12 of class 6. If not, you may try it out now. Paheli and Bozo had also set up the game by connecting an electric circuit as suggested in class 6. They had lots of fun trying it out with their families and friends. They enjoyed it so much that they decided to suggest it to a cousin of theirs who stay in a different town. So Paheli made a neat drawing showing how the various electric components were to be connected. Figure 14.1. Set up to check how steady your hand is. Can you draw this circuit conveniently? It makes Bojo wonder if there was an easier way to represent this electric component. 14.1 Symbol of electric components. Some common electric components can be represented by symbol in table 14.1. Some electric components and their symbols are shown. You may come across different symbols for these components in different books. However, in this book, we shall be using the symbols shown here. Look at the symbols carefully. In the symbols for the electric cells, notice that there is a large line and a shorter but thicker parallel line. Do you recall that an electric cell has a positive terminal and a negative terminal? In the symbol of electric cell, the longer line represents the positive terminal and the thicker or shorter line represent the negative terminal. For a switch, the on position and off position are represented by the symbol as shown. The wires used to connect the various components in the circuit are represented by lines. In the table 14.1, a battery and its symbols are also shown. Do you know what a battery is? Look at the symbol of a battery. Can you make out what a battery could be? For some of the activities, we may need more than one cell. So, we connect two or more cells together as shown in figure 14.2. Here, table 14.1 shows the symbol of some electric circuit component. First, electric cell. Second, electric bulb. Third, switch in on position. 4, switch in off position. 5, battery. 6, wire. Notice that the positive terminal of one cell is connected to the negative terminal of the next cell. Such a combination of two or more cells is called battery. Many devices such as torches, transistors, toys, TV remotes control use batteries. However, in some of these devices, the electric cells are not always placed one after the other as shown in figure 14.2. Sometimes the cells are placed side by side. Then how are the terminals of the cell connected? Look carefully inside the battery compartment of any device. There is usually a thick wire or a metal strip connecting the positive terminal of one cell to the negative terminal of the next cell. Figure 14.3. In order to help you to place the cells correctly in the battery compartment, plus and minus symbols are usually printed there. How can we connect the cells to prepare batteries for our activities? You may make a cell holder as shown in figure 14.4 using a wooden block, two iron strips and rubber bands. It is necessary. Here figure 14.2 A. Battery of 2 cells, and B. A battery of 4 cells. 14.3 Converting 2 cells together to make a battery. It is necessary that the rubber band hold the metal strip tightly. Figure 14.4 a cell holder, and 14.5 another type of cell holder. You could also buy cell holder from the market for making batteries of 2 or more electric cells. Place the cells in them properly such that the positive terminal of one cell is connected to the negative terminal of the next cell. Connect a piece of wire each to the two metal clips on the cell holder as shown in figure 14.5. Your battery is ready for use. The symbol used for representing a battery is shown in table 14.1. Let us now draw a circuit diagram of an electric circuit using symbols shown in table 14.1. Here one information is given. Paheli and Bozo wondered whether the batteries used in tractors, trucks and inverters are made from cells. Then why is it called battery? Can you help them to find the answer to this question? Activity 14.1. Make the electric circuit shown in figure 14.7. You used a similar circuit in class 6 to make an electric bulb glow. Do you remember that the bulb glows only when the switch is in the on position? The bulb glows as soon as the switch is moved to the on position. Copy the electric circuit in your notebook. Make also a circuit diagram of this circuit using symbol for the various electric component. Is your diagram similar to one shown in figure 14.8? It is much easier to draw a circuit diagram using symbols. Therefore, we generally represent an electric circuit by the circuit diagram. Figure 14.9 shows another circuit diagram. Is it identical to the circuit diagram shown in figure 14.8? In which way is it different? Would the bulb glow in this device's electric circuit? Recall that the bulb glows only when the switch is in the on position and the electric circuit is closed. Figure 14.7 an electric circuit, and figure 14.8 circuit diagram of an electric circuit shown in figure 14.7. Notice that the key or switch can be placed anywhere in the circuit. When the switch is in the on position, the circuit from the positive terminal of the battery to the negative terminal is complete. The circuit is then said to be closed and the current flow through the circuit instantly. When the switch is in the off position, the circuit is incomplete. It is said to be open. No current flows through any part of the circuit. In the bulb, there is a thin wire called the filament, which glows when an electric current passes through it. When the bulb gets fused, the filament is broken. Figure 14.9 another circuit diagram. Caution. Never touch a lighted electric bulb connected to the mains. It is very hot and your hand may get burnt badly. Do not experiment with the electric supply from the mains or a generator or an inverter. You may get an electric shock which may be dangerous. Use only electric cells for all the activities suggested here. If the filaments of the bulb is broken, would the circuit be complete? Would the bulb still glow? You might have noticed that a glowing electric bulb become warm. Do you know why? 14.2 Heating effect of electric current. Activity 14.2. Take an electric cell, a bulb, a switch, and a connecting wire. Make an electric circuit as shown in figure 14.9. This activity has to be done using only one cell. Keep the switch in the off position. Does the bulb glow? Touch the bulb. Now move the electric switch to the on position and let the bulb glow for a minute or so. Again touch the bulb. Do you feel any difference? After moving the switch back to the off position, touches the bulb again. Touch the bulb again. Activity 14.3. Make a circuit as shown in figure 14.10. Take about 10 cm long piece of nichrome wire and tie it between the nails. You can get nichrome wire from an electric repair shop, or you can use a piece of discarded coil of an electric heater. Touch the wire. Now switch on the current in the circuit by moving the switch to the on position. After a few seconds, touch the wire. Do not hold it for a long time. Switch off the current. Touch the wire again after a few minutes. You might have The wire gets hot when an electric current passes through it. This is the heating effect of the electric current. Can you think of any electric appliances where the heating effect of the electric current is used? Make a list of such appliances. Here figure 14.10 shows. You might have seen an electric room heater or an electric heater used for cooking. All these contain a coil of wire. This coil of wire is called an element. You may have noticed that when these appliances are switched on, after connecting to the electric supply, their filaments become red hot and give out heat. Bojo could not see element in an electric iron. Paheli told him that electrical appliances such as immersion heaters, hot plates, irons, geyser, electric kettles, hair dryer have elements inside them. Have you ever seen the elements in any appliances? Figure 14.12. Glowing filament of an electric bulb. Incandescent. The amount of heat produced in wire depends on its material, length and thickness. Thus, for different requirements, the wire of different materials are different length and thickness are used. The wire used for making electric circuit do not normally become hot. On the other hand, the elements of some electric appliances become so hot that they are easily visible. Incandescent electric bulb figure 14.12 are often used for lighting, but they also give heat. It means that a part of electricity consumed is used in produced heat. This is not desirable as it results in the wastage of electricity. The fluorescent tube lights and compact fluorescent lamp (CFLs) are better electricity efficient lighting source. Nowadays, the use of light emitting diode LED bulb is increasing. For producing a given intensity of light, LED bulb consume less electricity as compared to incandescent bulb or fluorescent tube or CFL. Thus, LED bulb are much electricity efficient and therefore being preferred. The filament, sorry, one more paragraph is there. It is advised to use electrical appliances and gadgets which are electricity efficient. Bureau of Indian Standard, New Delhi assign a standard mark and on products called ISI marks, which is an insurance of conformity to the specification given on the products. It is therefore suggested to use ISI mark products. Note: fluorescent tube and CFLs contain mercury vapor, toxic in nature. Therefore, damaged fluorescent therefore damaged fluorescent tube or CFL need to be disposed of safely. Figure 14.14 Fuse used in buildings. The filament of an electric bulb gets heated to such a high temperature that it starts glowing. If a large current passes through a wire, the wire may become so hot that it may even melt and break. But is it possible for a wire to melt and break? Let us check it out. Make the circuit we used for activity 14.3 again. However, replace the cell with a battery of 4 cells. Also, in place of the nichrome wire, tie a thin strand of steel wool. The steel wool is commonly used for cleaning utensils and is available in grocery shop. If there are any fans in the room, switch them off. Now, pass the current through the circuit for some time. Observe the strand of steel wool carefully. Note what happens. Does the strength of steel wool melt and breaks? Wires made from some special materials melt quickly and break when large electricity current are passed through them. These are used for making electric fuses. Figure 14.14. All buildings' fuses are inserted in all electric circuits. There is a maximum limit on the current which can safely flow through a circuit. If by accident the current exceeds this safe limit, the wire may become overheated and may causes fire. If a proper fuse is there in the circuit, it will blow off and break the circuit. A fuse is thus a safety device which prevents damage to electrical circuits and possible fire. Caution: never try to investigate an electric fuse connected to the main circuit on your own. You may, however, visit an electric repair shop and compare the burnt out fuses with the new ones. One reason for excessive current in electrical circuit is the direct touching of wire. This happens if the insulation on the wire has come off due to the wear and tear. This may cause a short circuit. Another reason for excessive current can be the connection of many devices to a single socket. This may cause overload in the circuit. You might have read report in newspaper about fire caused by the short circuit and overload. This day, miniature circuit breaker MCB are increasingly being used in place of fuses. There are switches which automatically turn off when current in a circuit exceeds the safe limit. You turns them on and the circuit is once again completed. Look for ISI mark on MCBs also. Figure 14.16 Miniature Circuit Breaker MCB. Caution: always use proper fuses which have been specified for particular applications carrying ISI marks. Never use just any wire or strip of metal in place of fuse. Fuses of different kind are used for different purposes. Figure 14.14 shows fuses used in our houses. Fuses shown in figure 1.14.15 are generally used in electrical appliances. We observed that heating effect of an electric current and learned how we use it to our advantage. Does the electric current have other effects also? 14.3 Magnetic effect of electric current. Activity 14.5 Take the cardboard tray from inside a discarded matchbox. Wrap an electric wire a few times around the cardboard tray. Place a small compass needle inside it. Now connect the free end of this wire to an electric cell through a switch as shown in figure 14.17. Note the direction in which the compass needle is pointed. Bring a bar magnet near the compass needle. Observe what happens. Now, while watching the compass needle carefully, move the switch to the on position. Figure 14.18 Hans Christian Ørsted. What do you observe? Does the compass needle deflect? Move the switch back to the off position. Does the compass needle come back to its initial position? Repeat the experiment a few times. What does this experiment indicate? We know that the needle of the compass is a teeny magnet which points in north-south direction. When we bring a magnet close to it, the needle gets deflected. We have also seen that the compass needle gets deflected when the current flow in nearby wire. Can you connect the two observations? When the current flows through a wire, does the wire behave like a magnet? This is what a scientist called Hans Christian Ørsted, figure 14.18, also wondered. He was the first person who noticed the deflection of compass needle every time the current was passed through the wire. So, when electric current passes through a wire, it behaves like a magnet. This is the magnetic effect of the electric current. In fact, an electric current can be used to make magnets. Do you find it too surprising? Let us try it out. Figure 14.19 An electromagnet. Remember not to switch on the current for more than a few seconds at a time. The electromagnet weakens the cells quickly if it left connected. 14.4 Electromagnet. Activity 14.6 Take around 75 cm long piece of insulated plastic or cloth covered or enameled flexible wire and an iron nails, say about 6 to 10 cm long. Wind the wire tightly around the nail in the form of a coil. Connect the free ends of the wire to the terminals of a cell through a switch as shown in figure 14.19. Place some pins on or near the end of the nail. Now switch on the current. What happens? Do the pins cling to the tip of a nail? Switch off the current. Are the pins still clinging to the end of the nails? The coil in the above activity behaves like a magnet when electric current flows through it. When the electric current is switched off, the coil generally loses its magnetism. Such coils are called electromagnets. The electromagnets can be made very strong and can lift very heavy loads. Do you remember the crane about which you read in chapter 13 of class 6? The end of such a crane has a strong electromagnets attached to it. The electromagnets are also used to separate magnetic materials from the junk. Doctors use teeny electromagnets to take out small pieces of magnetic material that have accidentally fallen in the ice. Many toys also have electromagnets inside them. 14.5 Electric bell. We are quite familiar with an electric bell. It has an electromagnet in it. Let us see how it works. Figure 14.20 shows the circuit of an electric bell. It consists of a coil of wire wound on the iron piece. The coil acts as an electromagnet. An iron strip with a hammer at one end is kept closed to the electromagnets. Here figure 14.20 circuits of an electric bell. There is contact screw near the iron strip. When the iron strip is in contact with the screw, the current flows through the coil, which becomes an electromagnet. It then pulls the iron strip. In the process, the hammer at the end of the strip strike the gong of the bells to produce a sound. However, when an electromagnet pulls the iron strip, it also breaks the circuit. The current through the coil stops flowing. Will the coil remains an electromagnet? The coil is no longer an electromagnet. It no longer attracts the iron strip. The iron strip comes back to its original position and touches the contact screw again. This completes the circuit. The current flows in the coil and the hammers strike the gong again. This process is repeated in quick succession. The hammer strikes the gong every time the circuit is completed. This is how the bell rings. Keyword: battery, electric cell, heating effect of current, circuit diagram, electromagnet, magnetic effect of current, electric component, fuse. दिस इज़ द एंड ऑफ द चैप्टर। तो अगले क्लास में हम नेक्स्ट चैप्टर के बारे में पढ़ेंगे। तब तक के लिए थैंक यू।